How can a search engine return a page which is barely relevant to the query? Likewise, how can it omit results which seem to provide the exact information requested? In semantic matching, climbing the tree for correct and relevant query results, we address this problem and suggest a solution. Born to serve an almost encyclopedic role, the Internet has burgeoned into a compelling and pervasive part of daily existence. As industrial, architectural, and algorithmic advances step into the stages coaxed from years of academia and research, the Internet offers exponentially greater capacities for service, social interaction, information, education, entertainment, and other real-life needs in various forms to an ever-expanding range of users. This explosion in the amount and complexity of data available on the web has been steadily mitigating the potency of keyword queries. How can a search engine understand the user's intent and browse through what in a relational database would be parallel to a huge collection of large unindexed single-column relations and return pages which will accurately satisfy the query? There are essentially three parts to this problem: determining query intent, classifying pages, and constructing an algorithm which will accurately rank pages to match to a query. This problem is well known and much researched, but none of these works, to our knowledge, have proposed a solution which will be scalable and address general domains. The main contribution to this paper is a novel matching algorithm to search based on semantic meaning instead of just text display. We know that words are more than a collection of characters. A word is an idea and assumes a place in a structure. A machine can match characters. Today, it cannot interpret an idea. What about a structure? Work has already been done to determine the syntactical value of a word, and our idea is to factor that structure value into the final matching value. We'd rank each page as related to the query by its semantic matching value, or SMV, and return pages in order of both SMV and straight text match. Specifically, we'd construct a weighted tree for the query based on the semantics of the word. Every word in the query will be a leaf node in the tree, and each leaf node will have as parents all the other words which fall into the same category as the word on the leaf node. Each of these words will have as parents the category it falls into, and this pattern will continue until the root node object, the category to which all words belong. The tree will be weighted, with each subsequently ascending level having a higher weight and thus incurring a heavier penalty on the words from the web page which match nodes at that level. So here's a sample query tree, and each page will be represented by a similar tree, and each word on the page will earn the weight of the node it matches to. The total matching weight of a page will be the cumulative value of all the weights earned by its words, and pages will be ranked by TMW ascending. So a page with a TMW value of 0 will be an exact match. So here we have the query of the word red, and a word blue on a web page will incur the penalty of the weight at level 1. A query entered into a search engine will be sent to the semantic tree engine to be parsed into a tree. The STE outputs a constructed tree to the semantic search engine, which matches the tree against the repository of web pages in their tree to determine a TMW. Here we have a Google search page sending the query to the STE, and the output tree being matched in the SSE to find the SMV distance. So here's our tree construction algorithm and our algorithm to assign node level weights, which can be proven to take O of n log n time, and our key algorithm to match SMVs. The points to note are that weights are ranked in ascending order, and text matching is favored over semantic matching. We've done this in C#. Our platform is the web. Let's look at our prototype. So here we have a search engine. Let's query for the word red and search for it. We open a viewer, navigate to the file whose path we were given, and here's our tree. To see it visually, let's look at this. And we can see that the leaf node is the word from our query, and each ascending level which will be assigned a higher weight. Let's look at a more complex query. How about house for rent? We'll search that. go to the viewer, navigate to the file, and look at the visual representation. And here we have our more complex query tree. The standing issues which remain are completing the prototype and then seeing how we can expand WordNet's ontology, and also how we can construct a tree to strip out duplicate layers, build a web repository, and most importantly determine, will semantics actually show a true representation? Thank you.